Okay, so it's time for the last talk in today's agenda. I hope you have enough energy and power to hear about awesome performance improvements in the .NET 6. Today, it's right now it's evening in Moscow and St. Petersburg, but it's morning in your time zone, Steve, right?
It is, yeah. I'm near Boston, so it's 11:30.
Oh, 11:30. Awesome. So you are full of energy and ready for the talk?
I've had 4 cups of coffee. I'm ready to go.
Awesome. Awesome. On this conference, we have several people from Microsoft. We have Igor, we have Kunal, we have Adam, and of course we have you. And all of you are telling us awesome things that you do in Microsoft and improving .NET, making it better. And could you say a few words about your primary role, what are you doing in .NET?
Yeah, sure. So I've been working at Microsoft for over 20 years now. I've been in and around .NET for a large chunk of it. I joined the .NET team kind of proper, just as we were thinking about creating this open source cross-platform version of .NET. And so I kind of jumped on board and helped to make that a reality. That was .NET Core, now .NET 6. I spend most of my time sort of overseeing the libraries that make up .NET, ensuring kind of a good direction for them, quality, that we're doing all the right things for all the right people. But I also have a particular focus on performance up and down the stack. Whether it's in the runtime or the libraries or higher level with ASP.NET or wherever. So that's how I spend most of my time.
Awesome. Awesome. Recently, you have published a blog post with a list of all performance improvements in .NET 6, and this post is tremendous. I have tried to read it several times, and I guess I'm in the middle of it, but I just don't have enough time and mental energy to process all of these awesome features. So I hope you are going to tell a brief introduction in what's going on there, right?
Yeah, so the blog post sort of summarizes several hundred of the many more than that performance improvements in .NET 6. For this talk, obviously, there is no way I can go through anywhere close to that. You would all be extremely bored. So instead, what I've done is I've pulled out a few representative examples, not necessarily the biggest ones, not necessarily the best ones, but ones that in particular sort of represent a category of improvements that are also relevant if you think about those categories when thinking about your own applications, how you might be able to apply similar performance improvements in whatever area of your application that's relevant.
Cool, cool. So I guess, so I want to remind all the people in the audience that you could ask any questions in our Telegram chat, and please join discussion just right after the talk. You could also ask any question there. And I guess it's time to start your presentation, Steven.
Excellent. Well, thank you very much. Hello, everyone. Good evening to, I guess, most of you, or afternoon, morning, if you're somewhere else in the world other than Russia. It is exciting to be here. I love talking about performance. I love talking about .NET, and in particular now, .NET 6. As Andre alluded to, and as we were just talking about, .NET 6 is absolutely a huge release when it comes to performance across the product, whether it's the runtime, the core libraries, Windows Forms, WPF, ASP.NET, everything has seen monstrous improvements across the board. When I was going through kind of looking back over the last year to see what's actually made it into the release, there's been close to 7,000 PRs into our open source repos for .NET that contributed to this release. And hundreds of them were specifically about performance, not necessarily big changes. Some of them are removing an allocation here. Some of them are improving a hot loop there. Others are completely overhauling some system to make it X times faster. But they all move the needle, improve the performance of the platform in one way, shape, or form. And what's really exciting for me is while certainly a lot of them come from folks on the .NET team or elsewhere at Microsoft, going on close to 20% of them actually come from folks outside of Microsoft who find something that's important to them, submit PRs to fix it, and they get merged, and it improves the state of the world for everyone. So I would certainly encourage, if any of you watching this have some pet problem that you'd really like to see improved in .NET, please come to .NET Runtime, come to .NET ASP.NET Core, come to any of our repos and get involved. We'd love to have you. Now, Andre alluded to this blog post I wrote. It is quite long because there's just so much to cover. I also try and not just have a list of links, but actually explain what the changes are and why they're relevant. So obviously, we're not going to cover all of them here. I'd encourage any of you who are interested to go and read the blog post after the fact. If you just search for performance improvements in .NET 6, it should be the top results in your search engine. What I am going to do, as I mentioned, is kind of go through a few specific examples from, in particular, around the libraries, because I know Igor did a separate talk on CodeGen. Kunal did one on CodeGen as well. Adam talked about file I/O. So I'm going to sort of pick some other examples and not just show what they are, but kind of categorize them and explain why they're relevant and how you can kind of translate the kinds of improvements we made to your own improvements in your own application. Because it's nice to hear about some improvements others did. It's even better when you can take advantage of them implicitly by using whatever it was they did, but it's even better when you can then take the learnings from that and apply them yourselves. And because I was writing this presentation relatively late at night, and I've been watching a decent number of Friends reruns while trying to stay awake for various reasons, I decided to add a little bit of a Friends theme to this. So for those of you who haven't watched a lot of Friends episodes, every episode is titled The One and then something. The one after the Super Bowl, the one with the prom date, the one where somebody finds out, the one with two parts, etc. So I'm going to use this categorization throughout to kind of classify each of these improvements. So let's dive in. Let's start with threading, because threading is pervasive across all of our applications, and improvements to threading often end up kind of lifting all boats. If we make something faster in threading, we generally improve all applications. And a good example of this is cancellation token and cancellation token source, which every application, whether it knows it or not, is using under the covers and likely explicitly as part of being passed around to asynchronous operations. This is the one where we revisit past assumptions. And I call it that because it's really important anytime we're developing software to think about the decisions we made in the past and think about whether those were the right decisions then and whether they're the right decisions now. And cancellation token is a good example of this. We developed this over a decade ago when we were sort of in the beginning of the many-core era, and we expected that the phone in my pocket right now would have 1,000 cores by now, and my desktop would have thousands of cores. And if you had a cancellation token, it would be being beaten on by thousands and thousands of cores and threads all at the same time, causing massive contention. And as a result, cancellation token and cancellation source were implemented under the covers with a fairly sophisticated lock-free data structure that tried to minimize all of this contention. And that's awesome if you actually have that scenario. Turns out no one has that scenario, or it's extremely rare. The much more common case is you might have a little contention, a few threads here and there happen to access it at the same time. But for the most part, you create one, you pass it around through a serial sequence of operations. You might end up with multiple registrations with that cancellation token existing at the same time, but the actual act of registering didn't happen at the same time. And so we were paying all this overhead for this complicated data structure, both in maintainability, and lock-free data structures often end up, by their very nature, being heavier weight. They cost a little bit more to process, they cost a little bit more in memory. And by simplifying, by ripping it out, throwing it away, and creating something in its place, we could create something that was more maintainable, that actually met the scenarios of the day, and that was faster and lighter weight. And you can see that with a simple benchmark. Here I'm just creating a cancellation token source, registering with it, and unregistering with it. And if I look at some numbers from various releases, we can see on .NET Framework 4.8, this was taking about 150 nanoseconds and costing about 400 bytes of allocation. By the time we get to .NET 5, we basically cut that time in half. move the needle a little bit on allocation. But then when we get to .NET 6, we shave off another 20-ish%, and we end up decreasing allocation by approximately half. So we've made it lighter weight and faster by revisiting these assumptions and retuning the implementation to meet the scenarios of the day. And so that theme is something that's relevant for everyone to do as they're looking at their own code and evolving their own applications. Let's take another example from threading. This is the thread pool. Now, obviously, again, you can't get much more ubiquitous than the thread pool. Everyone uses the thread pool. It's underneath every application in .NET. And so every release, we try and improve the thread pool. And we've done so in particular in two ways in .NET 6. The first, you probably won't notice, and that is .NET 6 represents the culmination of rewriting portions of the thread pool that were in C and C++ in native code into C#. This is an effort we've been undertaking in a variety of areas of the libraries and core runtime, moving functionality that was native into managed. This provides us with a multitude of benefits. In the case of the thread pool, historically it's been split into, the worker pool in particular has been split into two parts. There's the managed portion that was responsible for the dispatch loop, where a thread would sit in a loop, wait for the next work item to arrive, process it, wait for the next work item to arrive, process it. So that was all in managed. And then in native was all of the logic around managing those threads, keeping track of how many threads we should have, deciding when to inject threads, deciding when to remove threads, and so on. We moved all of that logic in .NET 6 into managed code. So it's now all C#. This is good for us for a few reasons. One, it helps us to much more easily share that logic between various runtimes. So we can more easily share it between core CLR and Mono, for example. But it's also really valuable because we've found that both for ourselves and for others in the ecosystem, it's easier for us to innovate and experiment and be more agile when writing code in C# rather than when writing code in C, for example. And in particular, we're much more willing to accept churn and accept changes in C# at a faster rate because there's a whole class of security problems, buffer overruns and the like, that are much harder to experience in C#. You almost have to opt into them, where in C and C++ they're there. So there's all these benefits from moving this to manage, but in particular, it's allowed us to then do other things more quickly. And one of those things that we've done in .NET 6 is address a particular problem that has been prevalent with usage of the thread pool. And that is, while we really want workloads in .NET to be fully asynchronous top to bottom, that's how we achieve the best perf and the best scalability, we recognize that that's not always the case. There are workloads that do a lot of blocking. And in fact, there are workloads that do the worst kind of blocking, which is what we call sync over async. And this is where on a thread on the thread pool, you create some asynchronous operation, and then you block waiting for that asynchronous operation to complete. You queue some task returning method, you call it, and then you call task.wait or task.result or task.getAwaiter.results. And this is the kind of the kryptonite for the thread pool, because imagine the thread pool only had 4 threads and you queue 4 work items, each of which does this pattern. Each of them queues a work item and then blocks waiting for it to complete. And now imagine that each of those work items can't complete until they themselves put something back onto the thread pool, some sort of continuation or completion operation. We've now deadlocked the thread pool, right? Because we have 4 work items that are all blocked, wait on the only 4 threads in the pool, waiting for another thread in the pool to process something that allows them to wake up. So this is really bad. Now, there are mechanisms in the thread pool today to try and address this. Since the beginning of .NET, there's been this starvation detection mechanism that exists in the thread pool. And it's basically this separate gate thread that wakes up once or twice a second and looks at the queues and says, since the last time I looked, have any items been processed from the queue? If yes, great, I'm going to go to sleep for a little while. If no, oh my goodness, I'm starved, I'm deadlocked, I better introduce another thread. So it introduces another thread. That thread is able to hopefully pick off some work item, and running it and allows those other threads to be released. That's the goal. but it's very slow. Right? If you're only injecting a thread once per second, like this is a very slow way to ramp up to what you actually need. So let's take an example of this. Here I have a little bit of code. I'm creating, don't do this at home. This is a bad piece of code. I'm creating a task. I am then on my machine, which has 12 cores, I'm creating 48 work items, so processor count times 4, each of which, when run, immediately blocks waiting for that task to complete. Yeah. So I'm basically deadlocking the thread pool. And then only after I've created those 48 work items, I'm going to create one more 49th work item that will complete that task and unblock everyone. Okay. But because the global queue in the thread pool is FIFO, first in, first out, this last work item isn't going to run until all those others have completed, which means it won't run until the 49th thread gets injected into the thread pool. That's a problem. And so what's going to happen? Well, on my 12-core system, these 49 work items get queued. The thread pool, because I have 12 cores, will default to a minimum of 12 threads, which means immediately it's going to inject 12 threads to handle the first 12 work items. But then it's just going to sit there. All of its threads are blocked. Eventually, the gate thread will wake up and say, has anything changed in the queues? No? Oh, goodness, I better introduce another thread. So it introduces another thread, which immediately picks off the next work item, which immediately blocks. And now we're back exactly where we were, except with 36 work items remaining. And eventually the gate thread will introduce another thread and another thread. And 36-ish seconds later, it will finally introduce the thread that allows all of these other threads to get unblocked. And we can see that. If I run this on .NET 5, we can see that this is taking approximately 35, 36 seconds to complete because we're waiting for these threads to slowly be introduced to finally unblock everything. When I run this on .NET 6 now, you can see a very different picture. Now, rather than taking 35 seconds, now it's taking just over 1 second. And that's because this other change that we made in the pool now taught the thread pool about this kind of blocking. It taught the thread pool about waiting on tasks and allowed it to be much more aggressive about injecting threads to counteract this kind of activity. So we don't like this kind of workload, but we know it exists. We know it's a pain point for developers on .NET. And so we've introduced this yet another mechanism for injecting threads beyond the starvation mechanism and beyond a hill climbing mechanism I didn't talk about to help deal with this workload. So while we don't like it, this is the one where we just roll with it. Let's do one more example in the threading space, and then we'll move on from there. This is the one where we cache all the things. For those of you who know me or know the kinds of things I've worked on, async is really near and dear to my heart. It's something I've worked on since well before we introduced async and await into C# and .NET. When you have an async method, for example, this one, when it first awaits something that hasn't yet completed, any state that exists on the stack associated with this async method needs to be promoted to no longer be on the stack and instead be on the heap so that it can survive across this asynchronous operation and this thread going off and doing something else. We will no longer have the state on the stack because the thread has gone off to process something else. So we need it to be persisted on the heap. And that persistence requires some allocation. Now, in .NET Core, starting with .NET Core 2.1, we made significant improvements here compared to .NET Framework 4.8. As of .NET Core 2.1, this activity made async methods, kind of a bare bones async method, about 2x faster and allocate about 1/5 or 1/6 as much as was on .NET Framework. But you do still have that one allocation for the returned task, which we also add other state onto. This is something we would ideally like to avoid if at all possible. So around the same time as we were making those improvements, we also introduced value task and value task of T. The idea behind value task of T is it's a discriminated union between a T and a task of T. And what this lets us do is for asynchronous methods, which actually frequently complete synchronously, if you're handing back some T value, rather than having to allocate a task of T to wrap that T, we can instead just give you back this value task of T struct, wrapping the T value. So we don't have to allocate anything for the synchronously completing case. For the asynchronously completing case, we still end up having to allocate that task of t, and we give you back a value task of t that wraps the task object. Okay, so then we also introduced an interface, an iValue task source, an iValue task source of t. And we taught value task how to be either a t, a task of t, or a value task of t. A task of t, or an iValue task source of t. In doing so, we then allow objects to implement iValue task source of t, and reuse that object however they might like for subsequent operations, which enables reuse and pooling and allows you to avoid a per operation allocation. And we take advantage of that ourselves in things like system.NET sockets. So on socket, if you use receive async, as long as you're not making concurrent receive async calls on the same socket instance, which is super rare, we will end up reusing the same object every time you make a receive async call, allowing receive async to be amortized zero allocation, which is pretty nice. We do the same things in system IO pipelines and system threading channels and elsewhere. But in a case like the one that's on the slide, where you're creating an async method, the async method isn't taking advantage of this. If it completes synchronously, you don't allocate. But if it completes asynchronously, we will still allocate a task to back that value task. So one of the things we've done in .NET 6 is allow you to opt in to having us do that for you under the covers. So C# has a small tweak to it in C# 10 that now recognizes an attribute. And when it sees this attribute on an async method, rather than using the default infrastructure it would use for creating that returned task object, it instead uses the one that's specified in the attribute. And in .NET 6, we then also ship a few more implementations of these builders that support pooling. And you can see the effect of this. If I put up a screenshot from the .NET Allocation Profiler in Visual Studio, you can see for the version of this function that I invoked 1,000 times that didn't use the attribute, we ended up with 1,000 allocations for these 1,000 state machines. But in the version where I did apply the attribute, there's a single allocation for the single state machine, which we end up reusing every time this method is called. Now, pooling has its own costs. There is overhead to pooling, just like there's overhead to allocating and running the garbage collector. So this isn't necessarily a free lunch. You shouldn't just go and apply it everywhere. But as with anything for performance, it's one more tool in your tool belt. You can apply it to some of your async methods, see if it helps, and if it does, you're good to go. All right, let's move on from threading, and let's jump up the stack a little bit to system. Now, I know there's I believe there's a separate talk on random, so I'm only going to spend a little bit of time on this, but I think it's still worth highlighting to highlight the category. And this category is the one where it's no longer the 1980s. So we initially developed the .NET in the late 90s and early 2000s. And at that time, when something like system.random was developed, we went and found whatever algorithm made the most sense to use at that time. And it ended up using an algorithm that was a small derivation of the one Knuth wrote about in The Art of Programming in the early 80s. But at this point, that algorithm is now basically 40 years old, and a lot has changed in the area of pseudo-random number generators. So this is another example of kind of questioning past assumptions or revisiting things in the past. While it may have been great 20 years ago, there are better things now, and we can switch to them. Now, when it comes to random in particular, we've been a little cautious about making such changes because there are compatibility issues at play. If you just say new random, the base class, no seed, fine, we can do whatever we want to generate as good randomness and as fast as we want. But if you specify a seed or you derive from random, there are now compatibility issues. While we've documented with seeds that we reserve the right to change the algorithm in the future, in practice, lots of people have taken dependencies that given the same seed and the same sequence of next calls on the random with the same arguments, you're going to get the same deterministic sequence of results. Similarly, if you derive from random, and override the plethora of virtual methods that random exposes, you would probably be disappointed if in a previous release we were calling one of your methods and then we changed something and we stopped calling your method, your override in that next version. So we've been very hesitant to change random as a result. So what did we do? In this release, we basically carved out an area where we could innovate while maintaining compatibility for the other areas. In random's constructor, we now check, is this the base class and is the seed provided? If it is a base class and there's no seed, we can basically branch and do whatever we want. And so we can use the new algorithm there, and we can avoid unnecessary delegation between virtual methods that adds a lot of virtual method dispatch overhead. If you did provide a seed, but it's still the base class, okay, well, we still have to use the old algorithm, but we can avoid that delegation that's adding overhead. And then finally, there's the last category of, okay, well, this is a derived class. We need to maintain the kind of compatibility that we had in the past. But you can see the impact of this on a simple benchmark. Here I'm just constructing a new random. I'm creating basically about a 10 megabyte array of bytes, and then I'm calling next bytes to fill it. And whereas on .NET 5, this was taking about 70 microseconds, on .NET 6, it's taking about 1 microsecond. So basically 70 times faster, which speaks to why we wanted to make this kind of change. So it's, again, a good example of where in your own code base you can go and revisit previous decisions made. Maybe 5 years ago you made one choice that you would do differently today. There's a lot of value in revisiting those assumptions. Let's take another example from system. So this is the one where we're card counters at the instruction table. And what I basically mean by that is, in some cases, there's no better algorithm to use. You just need to sit down and stare at what code is being generated, the IL and the assembly, and revisit whether there are new primitives you're able to take advantage of, and just try and tune the heck out of the system and eliminate as much overhead as you possibly can. And we've done that repeatedly with things like GUID.parse, because parsing GUIDs and formatting GUIDs is a very common operation we see across .NET applications, including in the core libraries. So we did that in this release as well, taking advantage of some of the new types like nint and nuint to help the JIT do a little bit better, taking advantage of spans in a way that helps the JIT avoid bounds checking, and things like that. And you can see the net result of such a change just with a very simple benchmark where we're creating a new GUID and then repeatedly parsing it. And you can see on .NET Framework 4.8, this was taking about 250 nanoseconds. By the time we get to .NET 5, we've been able to decrease that by basically 3x to about 80 nanoseconds. But then even beyond that, going to .NET 6, there's yet another 2.5x, where we get that down to basically 30 nanoseconds. And while I can't promise this is going to continue the trend of improving in .NET 7, 30 nanoseconds is pretty darn fast for parsing a GUID. You better believe we're going to try. Because these are the kinds of things we just want to continually drill on in every release, try and make these primitives faster and faster and faster and faster. Let's take another example. These are some of the more interesting ones. These are the ones where we have our cake and eat it too. For those of you who don't know this English idiom, this is basically, this phrase basically means you both get to have something that you want, while spending it as well. So, I really want to improve perf, but I also really want this feature that's going to cost me some perf. So can I have the best of both worlds? And we faced this with datetime.utcnow and datetime.now. We had been working on driving down the cost of datetime UTC-now because it is used in hot loops for timing measurements and things like that. But along came a feature that we felt we had to add, and that was leap seconds. For those of you who don't know, like I didn't know back then, there's actually the concept of leap seconds that derives from, as I understand it, the fact that our Earth rotates at a non-constant speed. It slows down and speeds up over time. And this results in some inconsistencies between the various mechanisms by which we as humans measure time. And so the powers that be decided that every once in a while, we should fix that inconsistency by introducing one more second. So you can end up with a time like 11 hours, 32 minutes, and 60 seconds, which wouldn't otherwise happen. Now, when Windows added support for this, on Windows, the .NET implementation then took advantage of that and supported leap seconds. It's also supported on Linux, to be clear. But on Windows, it got about 2.5x slower or 3x slower. And you can see that with a little benchmark for UTC now, where on .NET Core 2.1, when I ran this was about 21 nanoseconds. And then when I ran it on .NET Core 3.0, which had this support for leap seconds, based on the support in Windows for leap seconds, this decreased to about 60 nanoseconds. So we left some perf on the table there. Thankfully, some of the devs working on .NET, in coordination with folks on Windows, figured out a caching scheme that allowed us to both have our cake and eat it too. We were able to still maintain support for leap seconds, but avoid this cost 99.999% of the time, such that amortized, we ended up essentially back where we were several releases ago while still supporting leap seconds. So a pretty nice success story. Let's take another example from system. And while I call this from system, it's more kind of to do with system, because this is really highlighting the fact that our team no longer wants to have folks working on .NET thinking just about what are the new APIs that I can add, or how can I make the existing APIs faster. We want to be thinking about a holistic picture for how developers best take advantage of that functionality. What are the pitfalls? Are there correctness issues we need developers to be aware of? Are there old functions they may have been using and they should start using newer functions? We want to help them with that migration. Are there ways that they could be using existing functions better? So starting with .NET 5, we started adding a whole bunch of analyzers to the .NET SDK, all built into the SDK. And we've continued that trend in .NET 6, and we'll continue it in .NET 7, where we add analyzers to help flag places in your code where you could do better. And that includes for performance. So here is just one example of a new analyzer showing up in .NET 6. Here I have a function called say hello that takes a quoted name, like Stephen in quotes, and its purpose is to say hello, Stephen, without the quotes. So the original code that was written concatenated hello plus the substring on quoted name. But now with spans, we could instead use quoted name.asSpan, and there's overloads of string.concat that don't just take strings, but take read-only spans of chars. And so this analyzer is saying, hey, what you're doing is fine, but if you were to just make these two tweaks, if you were to switch to using string concat and switch to using as span, you could eliminate half of your allocation by getting rid of that intermediate string. So there are a plethora of these analyzers. They're included in the SDK. They have different severity levels by default. So you can go and experiment with them, figure out which ones you want to promote to warnings or errors, figure out which ones you want to leave as suggestions in the IDE. And they can really help kind of up-level the code across your code base. So this is the one where we optimize your code for you. Now, and I say we, I really mean the global we, because a bunch of these analyzers were actually submitted by folks in the community, which is pretty exciting. Let's do another example, and this one is a very large category. This is the one where we vectorize. Vectorization means taking advantage of functionality in the hardware that lets you do more than one thing at the same time. So let's say I had an array of bytes, and I wanted to compare it to another array of bytes. I could walk those arrays and compare byte by byte by byte by byte. Or maybe I could kind of reinterpret those byte arrays as a span of longs or ulongs. And then I could read long by long by long. And effectively, because at the hardware level, comparing a byte and comparing a long basically take the same amount of time, I can do 8 times as much stuff in the same amount of time. And there are additional hardware instructions with these additional instruction sets like SSE2, SSSE3, AVX2, all the intrinsics that exist on ARM that allow you to do more than 8 bytes at a time. Maybe you do 16 at a time. Maybe you do 32 at a time. There are thousands of these instructions that allow you to do various operations, not just comparison. And so we've been taking advantage of these across the stack. And every release, we vectorize more and more stuff. So an example of that is with span.fill and array.fill. In a previous release, we actually did vectorize these for bytes. But let's say you had an array of chars. So here I have an array of 128 chars. This was not vectorized. So this operation in the past would walk character by character by character, setting the new character value into the array. Now we vectorize anything we can possibly vectorize as part of these operations. And you can see the impact of that with this benchmark. This was taking on .NET 5 about 56 nanoseconds to fill in each character by character. And now on .NET 6, because we're able to basically do many of these things at the same time, it's taking only 4 nanoseconds. There are plenty of other examples in this category. For example, we vectorized convert.toHex string. So now the process of creating a string of hexadecimal digits from a byte array is way faster as well. So another thing to look at, there are all these hardware intrinsics you can be taking advantage of. There are higher level APIs like Vector that allow you to take advantage of this. And it's a great way for certain kinds of operations to significantly boost your throughput. One more example from system. Actually, there'll be 2 more examples from system. But another one from system this is the one where we special case. Special casing is an incredibly powerful form of optimization. One that you have to be a little careful with, because special casing means basically checking for some condition, typically on inputs to your function. And if it meets certain criteria, then going down a faster path that you've been able to special case. The problem with special casing is if you don't meet that condition, you've still had to pay the cost of performing that check in the branch and so on, and don't get any of the benefits. So special casing is valuable when you have a really good sense of what your inputs are going to be and can special case the vastly common ones, or when you know that the condition you're checking is so cheap that it won't matter if you're paying that cost unnecessarily. But string.replace is a good example of this. You can see in this example here, I'm downloading from Project Gutenberg. I believe this is the complete works of Mark Twain. So a fairly sizable file. And I've got one benchmark that's yelling by replacing all of the periods with exclamation points, and another one that's concatenating by changing all the new line characters to be string.empty. Now, in the first example, the interesting thing to note is that both the input and the character to search for and the replacement character are both one character. And as a result, we can actually instead just delegate to a different overload of string.replace that actually works on characters rather than strings. And the nice thing about that one is already optimized in 2 specific ways. First, because we know that we're just replacing one character with another character, we know that the output string length will be identical to the input string length. And so we can do an upfront allocation for the new string and very fast copies and just replace the relevant characters that need to be replaced. It also allows us to do a very fast search for the character to be replaced using index of, which is already vectorized using these SIMD instructions. The second example, they're not the same length, but the first string is still one character long. So again, we can still special case it and use index of for a character to find the starting position. And you can see the impact of these 2 starting cases on this particular benchmark. You can see that whereas in .NET 5, this yell function was taking about 33 milliseconds, it basically got twice as fast in .NET 6 to about 17 milliseconds. And similar for the concat, it got about 30% faster. So again, the kind of things to look for as you're profiling your applications, if you're seeing the same input, the same kinds of input, and there's a way to special case them, it's a kind of optimization to consider. All right, last example from system before we move on. This is string interpolation. So string interpolation has been completely overhauled. This is the one where we reinvent the mechanism or reimagine the mechanism. We have done work in both C# and in .NET 6, C# 10 and .NET 6, to overhaul both how string interpolation works and what you can do with it. We've made it a lot more capable than it was in the past. So let's take a simple example. This function accepts a string builder and 4 integers, major, minor, build, and revision. But basically, we're appending a version number, a dotted version number onto a string builder. And you can see we're doing that with string interpolation. So we're calling string builder.append major.minor.revision. Now, if I look and see what code this actually generates, in .NET 5 and C# 9, you can see the C# compiler lowers this to a call to string.format with the composite format string, and then these 4 integer arguments. Now, there isn't actually an overload of string.format that takes a string and 4 arguments. What there is an object params array. So if I look at this and say sharplab.io, I can see that what's actually generated here is we're allocating an object array, then we're boxing these 4 integers and storing them into the array. then we're passing that along with the composite string to string.format, which needs to, every time you call it, parse that composite string. For each of the objects that it's filling in, it needs to do a type check, maybe for an interface, make an interface call or a virtual call to get the string or whatever it is it needs to use to populate this string. And at the end of the day, we then end up with a string that we turn around and append onto the string builder, even though what we really wanted from the start was just appending these things directly to the string builder as we go. And in fact, that's exactly what we get with .NET 6 and C# 10. This is now the code that you get that's generated for .NET 6. You can see that because we added this one new overload for string builder.append that took a custom struct type that meets a pattern the C# compiler now looks for, the C# compiler was able to lower this to basically these append calls onto this struct that's just delegating under the covers into the string builder. So now we're just appending major as a generic integer method call, and then we're just appending the dot literal and so on. And you can see the impact of this when I run this on .NET 5 versus .NET 6. On .NET 5, this was taking about 160 nanoseconds and allocating about 192 bytes. On .NET 6, this was taking about 40 nanoseconds and not allocating anything because it's not having to allocate that params array, it's not having to box those objects, and it's not having to allocate that intermediate string. This is a very interesting area. There's a whole blog post dedicated to it. I have a link for it in the slides. I'd highly encourage you to go look at it, and it explains some of the really interesting things you can now do with string interpolation as well around conditional evaluation and the like. So please check that out. All right, moving on. Array pool. Array pool shows up everywhere. And for the most part, it does a really great job, especially with larger arrays for helping, a K or 4K arrays, bytes or chars or whatever, of helping to avoid lots of additional costs from the GC and lots of additional zeroing, because when you ask for an array from the GC, it has to make sure that it's been cleared out. However, this is the one where we remove the cliff because there's there's a dragon lurking in the array pool. At least there was prior to .NET 6. We can see where that dragon lives with this benchmark, where I've got one method that's asking for an array of 1024 times 1024 bytes, and then one that's asking for an array of 1024 times 1024 plus 1. And when I run this, we can see that on .NET 5, the difference between these is staggering. The .NET 5 numbers look okay. We're taking about 21 nanoseconds to rent and return this array, and it wasn't allocating anything. But with these 1 byte larger array, it's about 600 times as expensive, and it's allocating a megabyte on every call. And this is because there was a cliff. There was a hard-coded limit on how large the arrays could be that the array pool was willing to store. And this existed for historical reasons with the array pool, because when it was originally built, the array pool didn't have any built-in mechanism for forcefully getting rid of arrays that had been there for a while and no one was using. And we didn't want to end up with a situation where you rented a 100 megabyte array of foos or whatever T, and then returned that to the array pool, and it would stay there for the lifetime of the application and show up as a 100 megabyte leak. We have fixed that trimming problem. The array pool now is able to get rid of such things. And so we have also been able to fix that cliff by removing that 1 million item upper limit. And so now when you run this on .NET 6, you can see that regardless of whether it was the 1 million items or 1 million items plus 1, that you end up with the exact same amount of time and the exact same amount of allocation, which is 0. And this kind of, in your own code, think hard about these upper limits that you're putting in place, because if developers don't know about them, they can easily trip over them and have unexpected performance problems in their application. And if they do know about them, they end up having to work around them themselves, since you end up with all of these call sites having to work around the possibility that they might trip over this cliff, which is one of the reasons we focused on removing the cliff entirely. All right, moving on, file I/O. So I know Adam did a whole talk on this, so I'm just going to touch on it briefly, but I do want to touch on it again because this is one of my favorite changes in all of .NET 6. In large part because it's been plaguing us for 20 years since the beginning of .NET. This is the one where we make async actually async. Since the beginning of .NET, FileStream has exposed asynchronous functionality. It's dutifully implemented and overridden all of the async methods on Stream, and it's exposed the option on Windows for this file options.asynchronous, which tells Windows to use overlapped I/O instead of synchronous I/O. So it's done all the right things, except in the implementation where it hasn't. And you can see, if you look at various issues over the years, this is one from 5 years ago highlighting the fact that async reads are actually being turned into synchronous reads. Here's one highlighting that every time we make one of these read async calls, we're actually doing a seek, which is a synchronous operation. Here's one highlighting that write async calls are actually using blocking APIs. So even though we were trying to be async, we weren't. And here's one highlighting that filestream.flush async actually ends up doing synchronous writes. All of this just makes us very unhappy because async in general typically incurs a little bit more overhead than synchronous operations. You have to set up some additional stuff to be able to handle the callback and hand back a promise to the caller and so on. So we were paying all these costs and not getting any of the scalability benefits. But no more. This has been fixed quite nicely in .NET 6, both synchronous and asynchronous I/O on both Windows and Linux and Mac OS. It gets faster across the board, in some cases quite dramatically. So this is just a little benchmark. I've got a 10 megabyte file, and I'm reading it I actually don't have the chunk size on the screen, but I think this was either a 1K buffer or a 4K buffer, and I'm just reading the whole file in these 1K or 4K chunks. And you can see that on .NET Framework 4.8, this was taking about 350 milliseconds to do that read and allocating about 4 megabytes of stuff along the way. You can see that by the time we got to .NET Core 3.1, we'd made a substantial, maybe 25% dent in the throughput and cut off as well about 25% of the allocation. But by the time you then get to .NET 6, we've cut that dramatically to about basically doubling the throughput from .NET 5 to .NET 6 and all but eliminating the allocation along the way. So a pretty substantial change. I just saw a tweet yesterday from someone who was saying they actually thought their application wasn't running because it was so fast. They were reading files, writing files, and it completed so quickly they thought it wasn't actually generating the files they wanted it to. But it actually was. It was just so much faster than they had come to expect. So pretty cool. Let's move on. Another form of I/O, this one being networking. This is one where we stop doing unnecessary work. And it's another great category of stuff where if you can find ways to just stop doing things that were expensive that you didn't need to do, you can save a lot of time in your application. In this particular case, HTTP client ends up, when you access response headers, it ends up parsing and validating those response headers, even if at the end of the day, all you wanted was the raw string key and string value that you received. But we were still spending all this CPU overhead and allocation time doing these parsing and changing data structures and whatnot. So for .NET 6, we added this new property on the HTTP headers type that gives you back a non-validated collection. You can query this, you can enumerate it, and this is doing the least amount of work it possibly can. So it's not validating, it's not parsing, it's just trying to give you back the raw data that it received. And with this particular example, where over loopback, I'm making an HTTP request to a local server, getting back a response with 10 or 15 response headers and enumerating them. When I do it using the original headers property, this is taking about 83 microseconds. When I just add on non-validated to skip all of that parsing and validation logic, you can see it drops by about 20% and also shaves off about 30% of the allocation, all by avoiding work that, for my purposes, I didn't have to do in the first place. So another really nice category of ways that you can improve performance. Let's take another example. This is the one where we make new faster. And it's highlighting that there are certain things that we can do that might affect people that don't even know they're using this functionality. So, there's a certain number of people doing fairly advanced things that use activator.createInstance directly. There's a much larger category of people that use the new constraint in C# and don't even realize that under the covers, when you use the new constraint, you're actually causing the C# compiler to output a call to activator.createInstance. That's how the C# compiler implements use of the new constraint. So if we make activator.createInstance faster, we make this kind of usage of C# faster as well. And that's exactly what we did by employing some better approaches to caching and reuse and finding better ways to find and invoke the constructor. We've been able to go from about 50 nanoseconds for this operation on .NET Framework 4.8 down to, on .NET 5, basically cut it in half to about 26 nanoseconds, and then .NET 6 under 10 nanoseconds to construct and initialize this object via activator.createInstance via using new with the new constraint. One more example from reflection, and this is the one where we get faster at self-defense. What do I mean by self-defense here? Well, when you invoke something via reflection, you're giving, excuse me, you're giving the runtime an array of arguments to pass to the target method. But the runtime can't trust that those objects actually match up with the types that the method is expecting. It needs to do some validation on those objects to ensure that it's not violating type safety. But if it just validated them in place, it's using the caller's array. The moment after it validated those objects were the right one, some other thread with access to that array could come along, change the object, and still cause type safety to be violated. So what does the runtime do? It makes a defensive copy of that array and only then validates on that copy. Well, now taking advantage of spans and being able to stack allocate spans and so on, the runtime now for up to a certain number of arguments will actually stack allocate that defensive span rather than heap allocating that defensive array. And we can see the impact of that with a benchmark like this. The caller is still allocating a new two-element object, but when the runtime actually goes to execute this, you can see on .NET 5, this was taking 140 nanoseconds and allocating about 104 bytes. And then on .NET 6, we've been able to cut about 15, 20% from CPU, but also have effectively the allocation because we're not having to make that heap allocated copy. All right, a few more areas and then we'll wrap up. Link. Link is one of those areas where everyone uses it, and we have a love-hate relationship with it because it makes certain code super easy to write and it looks really nice. But if you use it on hot paths, there's some overhead associated with Link that you incur. Now, we try really hard to drive that overhead down as much as possible. And so we still invest in optimizing things like sequence equal. So this is the one where we go right to ludicrous speed. For those of you who like Mel Brooks movies, you'll understand the reference. We have been able to, we didn't directly vectorize sequence equal, but what we did is we special cased a particular set of inputs that we could then used to call some other method that already exists that was vectorized. And we can see the impact of this. If I give sequence equal arrays or of a vectorizable type, or I give it lists of a vectorizable type, you can now see the impact. Here I've got two integer arrays, each of 1 million elements. And when I call sequence equal on this, not only with .NET 5 had we basically doubled our throughput since .NET Framework 4.8, but .NET 6 is about 50 times faster than .NET 5 because it's now able to vectorize this comparison operation rather than for each element having to iterate with multiple interface calls through these enumerable sequences. One more example from Link, and this is the one where we stop duplicating code. Another example of questioning past assumptions. In the past, when Link was originally written, apparently hashset was viewed as being a little bit too heavyweight. So a stripped down version of hashset was created in Link for use by Link's purposes. And at the time, it was probably faster. But since then, we've invested heavily in both dictionary and hashset has gotten way faster than it used to be, especially as of .NET 5, to the point where hashset is actually much faster and lighter weight than the one that was built into Link initially. So what did we do? We just deleted the code from Link and started using the built-in hashset. And you can see the impact of that on something like distinct, which under the covers uses a set to eliminate duplicates. And when I ran this on .NET 5, this took about 5 milliseconds and allocated about 5 megabytes. And just by switching the underlying type we were using on .NET 6, it took about 2.5 milliseconds and allocated way less at about 2 megabytes. All right, 2 more examples and then we'll wrap up. One of these is in the crypto space, and I like to call this one the one where we stop being lazy, because it highlights that sometimes us as developers can get a little bit lazy and put off for another day something that we don't think is particularly relevant. And we don't necessarily realize how much we're leaving on the table, how much performance we could have gained by addressing it. So there is a type in the crypto space called Toub base64 transform. It implements the iCrypto transform interface and can be plugged into CryptoStream to base64 encode some input using the crypto APIs. And there's this function called transform block, which takes some input bytes and then an output array to write those into. And you could pass in 1,000,000 bytes in a space for all of the output. And in theory, we should be able to do that in one fell swoop. But if you look at this particular comment, you'll see that this developer decided that it probably wasn't a big deal. For now, we'll only convert 3 bytes. So we'll take 3 bytes, convert it to 4, and no matter how many you gave us, we're only going to do 3, which means that we're not benefiting from being able to, say, vectorize the entire input that was given to us, even though the function this method is calling under the covers does actually vectorize. So we fixed that. We did a little bit of math to figure out exactly how much we could pass into the underlying function rather than just passing in 3. And the net results are staggering. You can see here I've got a 10 megabyte input. I'm base64 encoding that using Toub base64 transform. And whereas on .NET 5, this was taking about 150 milliseconds, on .NET 6, this is taking about 2 milliseconds. So way, 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 way faster. And that was already way faster than on .NET Framework 4.8, and way less allocation because of changes in previous releases around CryptoStream itself. All right, last example. And this is the one where we build it at, build time. There are lots of systems that use reflection to analyze things at runtime, and then often reflection emit optimized code paths to use for those inputs. This was the case with JSON Serializer, for example, where it would use reflection emit to generate custom serialization routines for the particular types that were being serialized. Now with Roslyn source generators, we can do all of that work at build time rather than having to spend any memory working set or CPU overhead or even load reflection emit at all to do all that work at startup or whenever the types were first seen. So you can play around with this. This is part of the SDK. You just attribute your types with the relevant thing, and the code generator goes to work spitting out this functionality. There are 2 of these source generators built into .NET 6. There's one for JSON. There's one for logging, for generating logging methods automatically for you with all the best practices. And you can expect that in .NET 7, we're going to be continuing this trend. We already have 2 more checked into .NET Runtime Main for .NET 7, one around DLL imports to avoid the runtime having to do all the marshalling stub generation at runtime. We can just do that at build time instead. And one for regular expressions, where today you might specify regex options.compiled. That causes the regex constructor to do a whole lot of additional work to reflection emit an optimized implementation for your particular regex. We can now, at build time, generate the C# for that regular expression and even spend more time optimizing it at build time than we were allowing ourselves budget for at runtime. So there's a lot more of these generators coming in .NET 7, and it's a great thing for you yourselves in your own projects to start exploring and find ways to do as much as possible at build time once, rather than every single time your applications run, paying for that in startup overhead, additional execution time on every run. So with that, that is my allotted time. I will make one final plea for folks to, if they're interested in this topic, to please go read this Performance Improvements in .NET 6 blog post. It is quite lengthy. I spent a lot of time not only enumerating about 400 perf improvements in the runtime, but also kind of explaining the what and the why behind them and trying to educate along the way about how these various runtime systems work. But hopefully it's worth your time. Hopefully it's worth the read. And if you like it, please let me know. If you don't like it, please let me know that too. I'd love to learn for next time, because I fully plan to do this for .NET 7 as well. And with that, thank you all very much. I appreciate it.
Thanks, Steve, for the awesome talk and for all of these awesome performance improvements in .NET 6, and it's really amazing.
My pleasure. Thank you.
And now I want to invite all the people who have any questions to Steve to the discussion in Zoom. Please join us. And for the rest of the people in the audience, I will see you tomorrow on another day of .next.